Welcome, Martina. Thank you. Thank you. My name is TuomasArtman, and I'm here to speak to you about Swift with hundreds of engineers. I'm the tech lead for frameworks and architecture, and yes, I'm jet lagged. I flew 15 hours, just as Benji said. But I do appreciate you having me up here and being able to sort of share some of the insights that Uber has done in the last year since we migrated over to Swift. Let me see if the clicker works. No, I don't think so. Oh, there you go. So our topic today is Swift with hundreds of engineers. I'm going to talk about our motivation of moving to Swift and building something new in Swift. I want to talk about the architecture that we chose when we did a full rewrite of our rider application. And I want to talk about some learnings that we experienced during this journey of rewriting our rider application. Who of you have used Uber before? Awesome. Who thinks it's better than Didi? Yes. Only a few. Well, good enough. So unfortunately, we sold our Uber business in China to Didi half a year ago. So you probably haven't seen the application that we've released since. We did a full rewrite of our rider application, the application that consumers use, and we launched it late last year. And I'm just going to show you a video of what it is, so you get an understanding of what the rewrite looks like that has been created fully in Swift. And I'm pressing the no. There you go. Yeah. No video. I'm sorry. So we'll just have to look at screenshots later. For some reason, this isn't playing. So what I want to do today is talk about our rewrites and talk about what we did in the last year. I have to go back in history a bit to talk to you about what the origin of Uber was. 4 years ago, this was the entire mobile team at Uber. 3 people sitting working on the rider application back in the day. And since we've grown quite a bit, today we have 400 mobile engineers across multiple offices in the world, all working on basically the 3 main applications that we have. The rider application, the driver application, and then Uber Eats, which is a restaurant servicing application. So coming from these 3 engineers who built the basis of what we've used for the past 4 years, there's a huge change in how we wanted to build the application today. As you can imagine, 3 engineers probably will build a very different application in terms of architecture than 400 engineers. And we did start running into problems with that architecture. As our team grew, we got more and more feature teams who were working on different functionality in the same application. And we started sort of stepping on each other's toes. We started to have problems with shipping features because you had to test multiple code paths from multiple teams. You had to make sure that your change doesn't break anybody else's code. So 3 years basically in after the previous rewrites, we started having problems with the architecture. And we tried to mitigate those by doing refactors. We tried to implement new paradigms in place. And we spent quite a bit of time in 2015 trying to mitigate against the downgrades of the application. So this is basically what the rider application used to look like. This is what these 3 people designed and wrote 4 years ago. And eventually, in addition to all the problems that we started having with the architecture itself, we started having problems with the user experience as well. In the second screen, you can see different teams fighting for screen real estate. If you start at the top, a team, this was Uber Eats, replaced just the Uber logo because they wanted some space up at the top to have a tab bar between taking a ride and ordering a meal. You had the next team try to expand the destination entry field because they wanted to force people to enter their destination more often before they took the trip. At the bottom, you see a banner trying to promote Uber Pool, trying to share a ride with somebody else. And then at the bottom, you see this horrible number of products, which is sort of maintained by the city teams. This is a screenshot of I think, Chicago, and you've got 9 different products set up by the team over there. And you can see that the UX doesn't scale with sort of the scaling of Uber. These products are not really legible, the map becomes very small, and the user experience started to degrade. So also in 2015, we started thinking about doing a full user experience refresh. Our designers went out and said, we just want to redo everything from scratch. And it was really the combination of having these architectural problems and wanting to make sure that we came up with an architecture that would make us become fast again, and having to do a full UX refresh. We decided to just drop everything that we had and start from scratch. Because we essentially realized that if you, with the current code base and the current architecture, wanted to implement the design that the designers wanted, it would take us longer to do it in the existing code base than to start a fully new code base. So, in effect, that's what we did. We said, let's just change everything. Let's throw everything out, start from scratch. So what do you do when you can't start a project from scratch, a new application? You start thinking about, well, what are really the goals of this new architecture that we want to build? What are the fundamental things that we want to make sure the application has now and in the future? So we set out to really set out some goals. We are always, goal-driven. We want to make sure that we can measure what we work on. So it was imperative for us to have goals for the architecture and for the rewrite. So the first goal we set, we want 4 nines of reliability. This is pretty inherent to Uber. All the backend services have an SLA of 4 nines, which means that it can be down for 53 minutes per year. If you're longer than that, you're no longer at 4 nines of reliability. And we wanted to implement that on the mobile side as well. We wanted to say 1 session out of 10,000 can crash, but no more. Otherwise, we're not 4 nines reliable, which is, I think, huge. I don't know about your numbers, but in previous companies where I've heard that the crash free rate usually is at maybe 99%, or 99.2 or 99.3, but never in sort of this range of 3 or 4 nines. So this was a huge goal for us. The second one that we wanted to say is, well, we want to support Uber's growth for years to come. We want to ensure that when we write something, we don't have to go back later, 2 years from now, 3 years from now, and do it all over again. We wanted to make sure that we lay something on the floor as a basis, and we can build on top of that for years to come. The fourth point was we wanted to provide Rails for both design and code. As you saw in the screenshot before, if you don't have Rails for design, you get to a messy user experience. If you don't say, how features are integrated into the main application in a very controlled manner, every team just goes out and does whatever they want and messes up the UX. But it is also true for code. If you don't tell your engineers how they should be implementing a feature, everybody will, do whatever they want. So we wanted to come up with, clear paradigms, clear ways of implementing features, and do that across code and design. Fourth, if you have 4 nines of reliability, how do you know, that it's actually 4 nines, and what do you do when you degrade from that SLA? You have to have monitoring. So we said, with this architecture that we built out, we want to have monitoring as a built-in first-class citizen. Engineers should not have to do anything in order to get automatic analytics, logging, debugging, and tracing out of the system. You should be able to build your feature, and somebody will tell you how that feature performs in terms of networking, startup speeds, frame rates, whatnot. And you should get analytics out of the box as well. When you implement a new feature, you should be able to look at your analytics dashboard and see how many people are using it, how does it affect business metrics. The fifth one was de-risking experimentation. Now that we set out the goal of having a very reliable application, that usually means that you have to slow down. If you want to maintain 4 nines of reliability, you essentially have to be very careful at publishing new features. But on the other hand, that's not really how Uber works. Uber moves very quickly. When we build new features, we really don't know if they're actually going to succeed. We don't know if they find a product market fit. So that's why we need to experiment. We need to ship features as quickly as possible and be able to experiment on them and then quickly roll them back if they don't work. And lastly, we wanted to make magic. We wanted performance second to none, we wanted fast startup times, and we wanted graceful degradation on low-end devices as well. And it turned on us at this point that Swift would probably provide us with quite a few of these points. We knew that Swift was at least a future-proof language, going to point 2, supporting Uber's growth for years to come. We knew that Swift was more reliable. We had a better type system that would catch errors at compile time more often. And we thought that Swift would also let us make more magic because it's faster. So we took the big step at that point to go with Swift. We didn't really have many expectations. Nobody had written a huge application in Swift. So we were a bit nervous, and it didn't go very well in the beginning. But eventually, I think we came to a good conclusion. We had to do a lot of work in order to make it work for us at this scale, but we'll get to those learnings in a second. So the second thing that we did when we started from scratch was to say, well, we do have Android engineers as well and Android applications. Could we come up with an architecture that supports both iOS and Android? Why is it usually 2 different architectures on these 2 platforms? What is inherently different about the architecture for these platforms? You do understand that when you go, for example, to the view layer, that things are different. But in terms of architecture, it really should be the same. So we said, let's pull in the Android team as well, and let's start working together with them to figure out what kind of architecture we should build so that we get to the same kind of naming. We use the same paradigms. We use RX Swift and RX Java. We use the same technologies and methodologies and naming as far as we can go, so that we essentially double the effectiveness of our teams. Because now you don't have to design a feature for iOS and Android separately, but you can have your iOS and Android engineers work out on the design together and then just implement it separately. And this was a huge win for us later on. We realized that the design of our functionality became so much faster because of this, because we essentially doubled the team at the design phase. So what we came up with is RIBS. RIBS is a new architecture, and we did a lot of work of figuring out whether an existing architecture would work for us, but it didn't. I could spend 2 hours just talking about RIBS, and if you've got interest, you can find me later and we can talk about it. But I want to very quickly just skim over the subject because we don't have much time, and I want to get to the learnings as well. So RIBS stands for Router, Interactor, there's a spelling mistake here, and Builder. The inherent idea that makes RIBS different from, say, Viper or MVC or MVVM is that it's routed on the business logic. All other architectures that we looked at are routed on the view tree. So your view is the main piece that runs your application. And we did a number of tries and figured that it doesn't work for us. We need to be able to separate features out better, and we need to route the entire applications on business logic. To give you an example, here's a very reduced tree of our application. We use something that we call state trees. This is also our so-called state machine. Each one of these points is an interactor. And an interactor is designed to make a very local, small decision and then branch out to either side or somewhere down the tree. If you start with the root of the application, the top-level interactor, it has only one thing that it does. It looks at whether we have a token. If we do, we go into the logged-in state. If we don't, we go into the logged-out state. That's all it does. It listens in on that change. It knows whenever that token changes, and it knows if a token is removed, we need to tear down the logged-in tree, and we need to go into logged-out. And when a token is added, we turn on the logged-out state, and we go into the logged-in state. Now, what that gives you is, on the right-hand side of the tree, on the logged-in side, you know that you're logged in. None of the other pieces ever need to handle tokens or user session or figuring out whether we're logged in or not. They know for a fact, because of the dependency tree that we use, that there is a token and they can use that token. Also, on the logged-out tree, you know for a fact that you can't call any APIs that need a token, because there is no token. You can't get it from anywhere. And the compiler will enforce this. If you moved something from the right side of the tree to the left side of the tree that needed a token, the compiler would tell you, well, I don't have a token, so screw you, I can't really do anything with this. To go a bit further, on the logged-in side, or the logged-in business logic, there again is a decision, a very global and very simple decision to be made. Obviously, the menu should always be there, so the menu is attached under that business logic unit. But depending on the state of the application, depending on the data that we have, we either are requesting a car, we want to get on a trip, or we are on a trip. And again, the business logic is super simple. It listens in on whether we are on trip or whether we are not on trip, and branches out to either side of the tree. How this relates to the UI then is, the UI is bound to the tree later on. So every single interactor and every single piece in this state graph can come with UI. The key thing to notice here is that none of the UI pieces know anything else about the application. So if you look at, for example, the shortcuts. The shortcuts are small pieces, and this is, by the way, the new application that I wanted to show you in the video, but couldn't. The shortcuts are quick shortcuts for where you want to go. They are interactors which have an associated view, and the view knows absolutely nothing about where they are, it doesn't know anything about parents, doesn't know anything about its children. It just sits there waiting to be pressed. When it's pressed, the shortcuts say up to the request interactor, hey, I was pressed. And that's all they do. So inherently, with this approach, your business logic is super isolated to very small pieces, and your application is created from these small pieces. So every single feature that you build, you can basically be sure that you're isolated from the rest of the application, and you don't have to test anybody else's features and functionality. That was a very quick intro into the architecture. I want to give you a quick timeline of how we did this, because I think this is interesting. Like if you at some point think about doing a refactor or a full rewrite of any application that you have, I would urge you to think about it in this way. Spend a ton of time up front before you start writing the application itself. So we said we're going to use half a year of messing around with the architectures, figuring out how we should be building these applications. And we did. We tried every single thing. We built our core flow in multiple architectures, and essentially came to the realization that we need to build our own architecture. Once we had it in place, we invited one team to join us. And we invited the core flow team to start building on top of the architecture, building out the basics of the application. And at that point, we were pretty happy with the architecture, but that first team gave us a lot of insight into things that we had missed. So the architecture was created with a team of 10 people, working for 6 months, and then basically 30 people joined to build out the core. And we realized that we had totally forgotten about UI animations, for example, or making sure that you can play animations, synchronized animations across multiple interactors. So we got a lot of insight into how to make things better by just working with one team. And within 2 months, we had nailed down these architectural changes, we had built out the core flow, and we knew that we were ready to invite everybody else on to the project. So in 3 months, we invited 200 engineers on both iOS and Android to port everything over from the old application into the new application. And in 3 months, we shipped, which is pretty amazing to me. Usually, when you hear stories about rewrites, they tend to not end well. You think that you can do it in 3 months, that will take you a year or something like that. But it took us 3 months to actually ship the application. We wrote over 10,000 Swift files, over 1 million lines of Swift code. So I dare say that it's the biggest application written in Swift that has been created to date. If you know of another one, I would be happy to know what it is. But it was a huge application. And we learned a lot from it. And this is sort of the gist that I want to impart on you. I want you to be aware of these problems that you might face when your teams grow. Because I think most of you are from small businesses, but I'm sure that everybody on your side wants to grow bigger and wants to expand your engineering team and wants to be, huge. So let's start with the good. What did we learn when using Swift last year for the writer application rewrite? Obviously, the language itself is great. I think you wouldn't be here if you thought otherwise. Coming from Objective-C it's definitely just a better language. We use all of the language features, and we're super happy with them. The second thing that we noticed is the crash free rate. So if you remember, we had a target of 99.99% crash-free rates. And how that's measured is per session. So if a user starts your application, that is one session from beginning to end. If you crash during that session, that's a crash. And 99.99% means that 99.99% of users don't crash during their session. So how did we do? Well, we did better than Android. Which is awesome. These are the figures the day we launched. So remember, we did a full rewrite of our application over 3 months with multiple teams, 200 engineers. We launched it. We had tested it internally, yes, by dogfooding it. We don't have any QA engineers. So we launched it out, and our crash free rate on the day of the launch was 99.97. Which means that 3 users out of 10,000 crashed. And I think this is pretty much industry leading. I haven't seen these figures anywhere else. Might be wrong, but these are pretty awesome. Android, on the other hand, didn't have such a good crash free rate, 99.90. Well, it's still good, but it's not as good as Swift. And we did a ton of tooling on the Android side in order to get there. We had static analysis to figure out nil pointer exceptions, and we spent a ton of time with industry-leading experts trying to figure out how we can catch all the problems that you can do in Java code. And essentially, we can sort of say that Swift is Java by a factor of 3 in reliability. Big asterisk there, not entirely true, might be different for you, but the big realization for us was that Swift is super reliable. if you do one thing, which is don't unconditionally unwrap anything. If you do this, you're screwed. You will crash, you will have programming mistakes, and your crash view rate will go down. So what we did from the get-go is we added linting to our project, and we said whenever somebody types an unconditional unwrap, you get an error, and you can't check your code in. CI will reject your diff. And to this day, we don't have a single unconditional unwrap in our code base. Now, you have to deal with these problems in different ways, and that's maybe the hard part. Sure, you don't crash, but your application can still get to a bad state if you don't handle these with some sort of error handling. If you get options that have nil values when you don't expect them, but at least we don't crash. The second thing we realized is that Android engineers with Swift are now super welcome to the project. With Objective-C, you couldn't get a single Java engineer to jump ship and start working in Objective-C. They just hated the language. With Swift, you're super close. If you guys have heard about Kotlin, which is a nice tool by nice coding language like JetBrains, who's one of the sponsors here, you can write Kotlin. You can use Kotlin to write Android applications, and Kotlin is basically identical to Swift, with a few exceptions here and there, but it looks pretty much the same. And Android engineers are super excited about Kotlin, and that's why they're super excited about Swift as well. So you can start getting Android engineers to work with you on the iOS projects as well. Now, to the meat of things, the bad, because we don't care really about the good sides. You want to have learnings about what it means, what you need to be prepared for when you go to such a big code base. The first thing that we found out is that testing is super hard. How many of you guys write unit tests? Too few dudes write unit tests. Otherwise, you don't know if your application works. If you write unit tests, you'll run into problems with Swift. Swift is not a dynamic language, which means when you write unit tests, you want to mock out all your dependencies, right? So when you're testing a business logic that, for example, writes to disk, you don't want to actually write to disk. You want to make sure that the business logic, when it does its thing, it writes a file to disk. With Swift, that's hard, because you can't use mocking libraries. There's no swizzling in Swift as you could with Objective-C. So you have to do something else. So if you consider this protocol, let's say a business logic that is using a storing instance that conforms to this protocol. It has a few functions, data for key, and store data for key. And let's say we want to make sure that when we have a business logic unit that when it receives a signal from somewhere, it writes something to disk. How do we do that in a unit test? Well, we need some sort of mock class, and the only way to do that in Swift is really to manually write it. You have to write a full implementation that conforms to this protocol, which is tedious work. In our architecture, everything is protocol-based, so we probably have something like, 12,000 protocols throughout the application, and writing a manual mock for each of these would be horrible. So we did what everybody would do. We just generate them. Because your mocks, basically, the protocols are pretty easily translatable to actual implementations. So we wrote a script called generate mocks, which goes through your entire code base and looks at wherever you can find these protocols using source state. And it figures out where there's a create mock on top of it. If there is, it's an indication for the tool to create an implementation for that mock. And what it does, it writes it out, and it creates a class for you, storing a mock that conforms to the storing protocol. And it creates all the handlers for you. First of all, it creates a full implementation. Data for key, stored data for key, and it creates a number of functions that you can use to implement those functions, variables that you can use to implement those functions if you want to verify the input for them. And it also gives you, right here, a variable that lets you count how many times that function has been called. And in the implementation, the counter is just incremented whenever you call it. Also, the implementation will return something valid back if you can compute what that value is. For example, if your function returns an optional, you also return nil in the default case. Or if it's an enum, we just return the first case in the enum. So with this tool, we can generate a 12 or 1,000 of protocol mocks automatically every single time when we want to. And for us, that means that we have about 200,000 lines of code that we don't have to write by hand, which is pretty awesome. And they're always maintained for us automatically. And then we can use unit tests to use these mocks and to figure out whether our business logic actually works. Now, the next bad thing are tooling issues. I don't know if you've seen this. Infinity indexing was a huge problem for us. Our project was so huge that this is our CPU. Source Kitten uses 328% of our CPU all the time, and it doesn't stop. It just sits there. The indexing never finishes. I watched it for like 4 hours, and no, it didn't finish. And it was a huge problem. The other thing what happened is, this is your ID. And this is not me typing slowly. This is me having typed out the line already, and now I'm waiting for the IDE to fill it out. So this was Xcode 8.2. Fortunately, things have become a bit better with 8.3, but you will run into these kinds of problems with your IDE when your team gets big and your code base gets huge. So what can we do about it? Well, the first thing that we thought of doing is just, throw Xcode into the trash and do something else. And we're still on this. But seriously, like, our engineers, they do like Xcode. So they wanna continue using it. We're on the side working on a separate implementation, a separate IDE to solve these issues. It's sort of a big shot. Let's see if it ever happens. But the one thing that you can do is upgrade to the latest and greatest Xcode as quickly as possible. Swift is evolving all the time, and it's becoming better all the time. So hopefully, with every version, you make progress. You can obviously use alternatives. You can say, again, sponsors right here, AppCode. AppCode is pretty okay for your Xcode development or your iOS development. Or what we did is we split up our application into multiple frameworks. So we don't have one big target anymore, but we have multiple small targets. And this helped us with all the IDE issues. And you can also disable indexing if you like. Some people did, but that's not very advisable. So the next bad thing is binary size. As you know, 100 megs is the limit to be able to download over the cellular network, and you have to, be below 100 megs. So why is Swift bad with binary size? A few things. Structs. Structs are allocated on the stack and can increase your binary size radically. We had all of our models as structs before, and our application binary was 150 megabytes larger because of that. So we don't no longer use structs in the model classes. Optionals. Similar problem. When you use optionals, binary, a lot of stuff gets written into the binary, which makes your binary larger. You get all these things that the compiler puts in to check whether it's nil or not nil and whatnot, which seems fair enough. If you just add one question mark to your code, the compiled code might be much larger. Generic specialization, although generics are awesome, whenever you use generics, you can incur a huge cost in specialization. where the compiler wants to optimize usage of generics that can increase your binary size. And obviously your Swift runtime libraries that come with Swift increase your binary size as well. So what can you do about it? You can wait for Swift 4. They're fixing it. We've talked with Apple engineers, and they know that it's a problem, and they have a few diffs out already landed on that branch to fix it. You can play around with optimization settings. Usually doesn't hurt much, but lastly, you can know where you're actually spending your binary size. And we did a tool that takes the output of your export build, all the dependencies, and just visualizes the binary size of every symbol and maps those back to folders. So we can drill, it's unfortunately not very visible, we can drill into all of our frameworks, and what it says here, it's a UI component that takes 44 kilobytes when it's compressed, when it's in the binary. So a nice visualization tool to let us understand where we're actually spending this, the binary size. I'm running a bit short on time, so I'm going to skim over these very quickly till I get to the last section. So another bad thing about Swift is startup speed. You incur a cost by loading up your dynamic libraries, and that can be painful when you work with Swift because you have the Swift standard libraries, which essentially take 250 milliseconds to load in pre-main. And then there's things about post-main that you can do with Swift, which we had a good understanding. So sorry about skipping this. I want to get to the ugly because this is also the meat of the presentation. The ugly on Swift is compile times, and I'm sure most of you agree it's super slow. So we went out in June 2016, and we asked our engineers, because it was becoming a problem. We asked our engineers, holistically considering all the positive and negative experience you've had with Swift, should we go forward with Swift or Objective-C? And this was the answer. 48% said Swift, 52% said Objective-C. And we're like, oh man, did we choose the wrong language? But we added a few questions in there as well. So if we drilled down into why, we understood that, well, the second question that we asked was, if you could change one thing about Swift that would make you change your mind, what would that be? And 23% said, well, if Swift just compiled faster, I would choose Swift. 7% additionally said, well, if it compiled faster and indexed faster, I would choose Swift. And lastly, 2% had debugging problems as well. But this looked much better already for us, and we were thinking that this is actually something we can do about it. We can fix it. We don't have to wait for Apple to fix it. So, what would we start looking into? Well, obviously, we can contribute back to Swift if we want to. Long path. We can add warnings on slow type inference. Starting a warn long function bodies equals 100. We'll spit out warnings whenever a function takes longer than 100 milliseconds to compile. Type inference can be super slow. Type inference means if you don't add a type to a variable or a block, but you let the compiler figure out what the type should be. So you can make mistakes with it. You can make the compiler take 10 seconds to compile a function. Just adding this warning will tell your engineers that they probably should add type information to some of the functions. And solver memory threshold, the same thing. You can actually generate an error if the solver, which does the type solving, takes more than 300 kilobytes to solve its thing. Lastly, what we did, we started combining files and figuring out whether we can get performance out of that in such a way. So we took all the 200 models that we had, and we put them into one file of 25,000 lines. And our compile time decreased from 1 minute 35 seconds to 17 seconds. We're like, hold on, what's this? It turns out that every single Swift process needs to do type checking, and all that type checking adds up. If you only have one Swift process that compiles a large amount of Swift code. It's much faster than multiple small processes compiling small parts of Swift. So we can solve this project right. We can use whole module optimization, because whole module optimization builds everything in one process. We knew that this wouldn't be able to optimize it other ways. But the problem with whole module optimization was that it will also optimize your code, which makes it super slow again. But there's a way around that. Our friends at Airbnb found this little trick, and it made our code compile 70% faster. And everybody else I've talked to as well. If you're not using this thing, start doing this, and your compile times will decrease by 50%, almost guaranteed. So you turn optimization level to none, and you add a user-defined flag called Swift_whole_module_optimization. You set it to yes, and the compiler will compile your Swift files in one go without optimizing it. So it's whole module optimization without the optimization. And everything will be super fast. So if you take one thing with you, take this. Lastly, we started to look at a tool called BUC. And BUC is a secure dependency management that does reliable incremental builds with a remote build cache. And if you are, willing to exchange your Xcode build for another build system, I urge you to look at BUC because it's awesome and it's super fast. What it does, we tried it first with Objective-C. Because of the remote build cache and the reliable incremental builds, you get huge increases in build times. So for our big project, in Objective-C, we saw a clean build be 4 times faster, incremental builds being 20 times faster. Android is even seeing bigger gains. There was no Swift support for BUC, so we added it. BUC is a project by Facebook. Do check it out if you're looking for a new build system and want to get some speed. But we added support for Swift into BUC. It's still out in a branch. There's a link, github.com/Facebook, BUC tree. We were pull requests. We hope to merge it soon into master. What we added is Xcode project file generation for BUC. So you can have BUC create a project file if you want to use Xcode to actually debug and test your application. And we added Swift support for BUC builds. So BUC can now build Swift files. And we're looking into adding BUC support for Xcode IDE as well. So when you hit command build, it would use BUC instead of Xcode build, which hopefully would get you speed increases of up to 4 times for incremental builds. So to wrap things up, I'm going like 2 minutes over my time already. What were the results of all of this work that we did? So looking at Swift, what did Swift help us with after coming back to sort of the goals that we had in the beginning? Reliability, definitely because of Swift. Support Libre's growth. Swift is really the language of the future. Providing Rails for both for code. Swift is much easier to comprehend. It has about a third of the verbosity of Objective-C. It's easier to implement patterns and enforce them. Monitoring is harder because you can't swizzle, so you have to find ways of generating code to monitor automatically. De-risking experimentation, again, going hand in hand with the reliability of Swift and the compiler. And making magic, Swift is more performant if you don't take into account the application startup speed. That gets slowed down because you have to load dynamic libraries. And we went back to our engineers in February this year, after we did all these changes, after we migrated to BUC, after we spent a ton of time figuring out the Xcode issues. And we asked them again the same question: which would they choose now? And the results look much better. 78% would want to stay with Swift, and only 22% thought that Objective-C was better for Uber. So, to end things, the takeaways. If your team is growing, what do you need to look out for? Keep an eye on your compile times. They will grow. The more code you have, the slower it will become. Monitor your binary sizes. Find out a way of using some sort of tooling in order to know where you're spending your time, where you're spending your binary size. Figure out how to unit test. I saw way too few hands up. You need to figure out a way to unit test, guys. Otherwise, you can't ship reliable applications. And then start using back. If you're having problems with build times, investigate back. But maybe the outcome for you guys is you probably will not start running into problems until you grow rapidly into a bigger team, until you have 50 engineers working on your projects. And when you do, your team is probably big enough to start handling these problems. And you probably can take a few engineers to start working on tooling and figuring out how we can make things better for the rest of your engineers. And that's pretty much it. Follow us on Uber GitHub.io. We do open source quite a few things. We've got a blog at eng.uber.com where we regularly talk about mobile stuff as well. And that's me. Thanks.